Greetings and welcome. In the last video session, we have discussed about the expression for shear stress and velocity distribution for a steady and laminar flow passing through a horizontal circular pipe. With continuation of that, we are going to see here expression for discharge passing through a horizontal circular pipe and average velocity of flow. Here are the two parts of this video session. So let us see first part, that is discharge passing through a circular pipe. To obtain expression for discharge passing through a total circular pipe, first of all here we consider a small fluid element. So that is shown here in the diagram. So here this is an elementary ring at radial distance small r with thickness small dr. Now we will consider a discharge passing through this shaded portion. So that is why this is a small discharge. Thus we denote this small discharge with notation dq. Now we know that for incompressible fluid, discharge is a product of area into velocity. So that is why here we can write for the small discharge expression or equation dq is equal to small area, this shaded area means dA, into u, that is a local velocity. Say this equation as a equation number 1. Now let us see terms of this equation 1 first, dA. So dA, area of elementary ring. So this area we can write by drawing this circular portion in a rectangular form. So length of this rectangular shape will be what? Circumference of this circle. So circumference of this circle with radius small r will be what? 2 pi r. Thickness of this is dr, that is elementary ring. Here this is another side, that is a small dr. Thus area of this rectangular shape will be what? Small dA is equal to 2 pi r into dr. In the last video session we have seen relation between local velocity and maximum velocity, that is u is equal to u max bracket 1 minus small r square divided by capital R square bracket complete. We will put expression for dA and u in equation number 1. Thus dq is equal to, at the place of dA we write 2 pi r dr, and for the u we use this u max into bracket 1 minus small r square by capital R square bracket complete. We will simplify this dq expression. So here we take this small r before the bracket. So in a next step 2 pi u max comes. This r which is taken here, this r we multiply with this bracket. This small dr we write at the end. Now processing of this r with the inside terms of the bracket, that is r into 1 small r into small r square, that is r cube divided by capital R square bracket complete. Remaining all the terms are written as it is. This is an expression for small discharge passing through elementary ring, that is a dq. To find the discharge passing through a total pipe, that is a q, we have to integrate this equation between the two limits. So their lower limit we consider as a radius 0, that is the center point of that pipe, and upper limit we consider that is a radius of that fluid element r, which is shown in the last slide in the diagram. So writing the Equation in integration form, integration of dq left side, right side this expression in the integration with limits, lower limit 0, upper limit capital R. As 2 pi into u max, these two terms are a constant, will be coming outside of the integration sign. Then here in the integration sign we get this bracket. Now taking integration of these two terms, first of all integration of small r, that is r square by 2. Integration of this term in that 1 upon capital R square as it is, integration of small r cube will be r raised to 4 divided by 4. This bracket, square bracket on that, this is a lower limit, this is the upper limit. Next step is putting these limits value in the expression. So for that, what generally we do, we put higher limit first of all and then we put lower limit. So there is a subtraction of higher limit and lower limit values. So first of all, this bracket with higher limit capital R at the place of small r, capital R square by 2 minus 1 upon capital R square as it is. At the place of this small r, this capital R, that is R raised to 4 by 4, minus in the second bracket we put the lower limit, that is a 0. Here we have put. Now in the second bracket 0, this will come 0, also this will come 0. So this total bracket will be 0. So there will be next step only this bracket simplification. So next step 2 pi into u max inside the bracket capital R square by 2 minus, here will be what simplification, that is cancellation of this square to this R raised to 4, remains R square divided by 4, bracket complete. Thus now the next step is what, taking the LCM. So in the LCM we take the product of 2 into 4 at the denominator, we take the cross multiplication at the numerator, means 4 into capital R square minus 2 into capital R square. Then subtraction of 4 minus 2, that is a 2 capital R square divided by 2 into 4. We keep as it is for the further process. Here cancellation of these 2 and 2, cancellation of these 2 with this 4 remains 2. Thus capital Q is equal to rest of the terms we write in the way pi divided by this 2 into u max into this capital R square. So this we say as equation number 2. This is what expression for discharge passing through a circular pipe. Now in the second part, that is for average velocity of a flow, as we have discussed already that continued equation Q is equal to AV. So discharge is equal to area into velocity. So arranging that equation in the form of velocity, we can write average velocity is equal to discharge upon area of that fluid element. So discharge we have obtained in the last session, in the last slide, that is pi by 2 u max into capital R square. Area of a fluid element, there we have seen that in the fluid element the radius of that fluid element is a capital R. For the circle, area is a pi into capital R square. So here cancellation of the terms, this pi into pi, this R square, capital R square to this capital R square. Rest of the terms are, here we write u max divided by 2. So we find here average velocity is equal to half u max. We say this as equation number 3. From this equation number 3 we can have a statement that average velocity is half of maximum velocity, or vice versa, maximum velocity will be twice of average velocity. Now we can write this average velocity in other way. So for that, from the last video session we have relation for maximum velocity in the term of pressure gradient that we will use here, minus 1 by 4 mu into pressure gradient to capital R square. Now here we will use this Umax expression and we will put this expression in equation number 3 at this place. Thus U average is equal to half into this expression we write here. So here minus sign will come here, 2 into 4 that is 8 with mu into pressure gradient into capital R square. This is a expression we say equation number 4, that is what for average velocity of a flow through a circular pipe. So in this way, in this video session, we have seen an expression for the discharge and average velocity of a flow passing through a horizontal circular pipe for a steady and laminar flow. Let us meet in the next video session. Thank you.